Hi everyone, thanks for attending. It is my great pleasure to introduce Théophile today. Théophile is a PhD student at INRIA in Paris, where he is co-advised by Karthikeyan Bhargavan and myself. Théophile's PhD topic is actually MLS, the messaging layer security, and this is work for which Théophile became a defender of the internet because we won the Internet Defense Prize last week at USENIX Security. So this is pretty impactful work, and I'm really glad that Théophile is getting a chance to talk about this. He'll be visiting throughout the rest of the week, and we'll both be around on Friday. So if you want to chat with Théophile, you can probably catch him on Friday morning. Théophile, the floor is yours.
Jonathan already talked about everything I wanted to say on my first slide. So yeah, so still he didn't give the link to the paper, so it's here.
Sorry.
Yeah, no problem. First I will talk about what is messaging layer security. So the idea is that something like 15 years ago, entered encryption was reserved to a restricted group of people that could afford the technical complexity associated with it. And nowadays, we can see in the media that entered encryption is becoming an essential feature of modern messaging applications. So state-of-the-art modern messaging applications like Signal guarantee confidentiality, meaning that the content of the conversation can be read only by the people involved in it. And in particular, it means that the content of the conversation cannot be read by the application servers, the internet provider, or the government. And so secure messaging applications are cryptographic protocols that execute for a very long period of time, sometimes a few years. And so we need to study what happens if one of the devices is compromised throughout the lifetime of the conversation, meaning that, for example, if the device is stolen or is seized by the police, and the private keys it stores are leaked. So state-of-the-art messaging applications ensure forward secrecy, meaning that if messages sent now stay secure even if one of the devices is compromised in the future. And they also guarantee post-compromise security, meaning that if a compromise happens now, after some period of healing, messaging is sent after will still be secure. And another feature of modern messaging applications is being able to communicate with groups. It's a feature that many people use. And group messaging security can rely on forward secrecy and post-compromise security. So when Eve joins a group, a property we may want is that she isn't able to decrypt messages sent before she joined, which looks a lot like forward secrecy. And when Eve leaves, a property we definitely want is that she cannot decrypt messages sent after she left. So about the state of the art of group messaging before MLS. So the state of the art was to use like a protocol that solved this problem between two people, which is a signal protocol, and use it pairwise. So there are two possibilities. Either each person, when sending a message to the group, send one message to each person of the group separately by using the corresponding signal channel, or they can use an optimization called sender keys, where each people in the group will say, "Oh, we will distribute a key that it will use to send messages to everyone in the group by using the pairwise signal channels. And so this is slow for large groups, because if you have n devices, then you have roughly n squared signal channels, which is slow, for example, at enterprise or university scale. And for example, so in the first version where you send one message to each person, it means that for a very large group, you need to encrypt one message to each person individually, which is slow. And in the sender keys protocol, if you want to recover from someone that was removed from the group, then it means that each person has to generate a new key and send it to everyone in the group, which needs a communication cost of n squared. So to design a better secure group messaging protocol, the IETF created the MLS working group for messaging layer security, and which recently published the MLS protocol as known as RFC 9420. So it was published last month, I think. And so the working group had the following design constraints. The protocol must be secure, so with confidentiality, but also forward secrecy and post-compromise security. It must be efficient, supporting large groups. It must be asynchronous, meaning that devices are allowed to be offline throughout the lifetime of the group. And it must also support dynamic groups, meaning that people can join and leave during the lifetime of the group. So this is a complex problem to solve that requires novel cryptographic work. And people tried to design such protocols in the past, but it's very easy to get wrong. And it did get wrong. For example, Matrix tried to design its own protocol by modifying, by adapting the signal protocol. But last year, security researchers found many embarrassing vulnerabilities. During the design of MLS, many variants of protocols were studied with different performance security trade-offs. And so here at the top, you can see the sender keys, which I talked about earlier, which has bad performance. And there are many variations of a protocol called TRICAM, which with different performance and security trade-offs. So because this is a complex program, this leads to a complex RFC, which is very big and is a result of an organic evolution through many commits and pull requests. Each one of these either so do editorial change, but also add feature, do some performance optimization, or fix some recently discovered attacks. So before I dive in the MLS internals, I will do a quick interlude and talk about the contribution in our paper. So roughly, we took the MLS protocol. We showed how to split it in 3 subprotocols, because MLS is described as a single monolithic protocol, which is a bit tough to understand. And so by splitting it in 3 independent subprotocols, each one of these is easier to understand. We can, so it helps for the implementation to have a nice modularized implementation, and also to have a nice security guarantee for each of these protocols. And so we found various design flaws, and we submitted fixes and other design improvements to the working group, which accepted the changes. And finally, we proved that the subprotocol, which we called TreeSync, is secure in the Dolevio model. So to do that, our methodology is the following. We take the MS protocol, so written in prose in English, we translate it into a specification in F-star, proof assistant that is developed right here. And so on this specification, we can do proofs, such as functional correctness proofs, like proving some invariant, for example. Then, to do security proofs, we must decide on a security model. We choose a symbolic model, and we do proofs with the DY star symbolic security framework. We instantiate the specification with DY star to obtain a symbolic implementation on which we can do security proofs. And we can also instantiate the specification with the verified cryptography library HackerStar to obtain a concrete implementation on which we can do interoperability tests. And we also used it to do a hackathon with the Skype team and try to integrate a prototype of secure groups inside Skype. So, which confirms that we can indeed use the specification, and it doesn't have any holes in the features it implements. So the next technical details here is that we use the same specification to do both proofs and interoperability tests. This is used to make sure that we make no mistakes when we translate MLS to F-star, because we don't want to prove security properties on a protocol that is not the true MLS, but some subtle variant of MLS. So we interoperate with other implementations. So there are 4 of them, one in C++, one in Rust, which are open source, and another proprietary one. Lastly, when doing the proofs, obviously it didn't work at the first try because what we tried to prove was not true. And so when doing security proofs, we found attacks that we fixed. And same when doing functional correctness proofs, we found bugs that we fixed. And when I say we fixed, what happened is that we submitted fix to the working group, and they were accepted because it's a collaborative effort at the IETF. Yeah.
Did Hackle have all the primitives that you needed to implement MLS?
Yes. So MLS has several cipher suits that it supports, and so HackerStar supports enough algorithm to implement some of the cipher suits, but doesn't implement all of them. So there are some weird elliptic curves like P3 something.
P256 we have, we're still missing P384 and P521. We're like adding them right now because Mozilla wants those in Hackle, so they're going to be there by the end of the year. But yeah, those were the 2 big omissions in Hackle.
Yeah, so the interoperability tests are on the cipher suite we support, obviously. So we don't support all of them, but still passing interoperability tests on one cipher suite is enough to have confidence that our F-star specification correctly reflects the MLS specification. So about the methodology, there are prior work that do similar things. So there is for example, the HackerStar library, which is so a verified implementation of cryptographic primitives, which is different because here we are proving a protocol which rely on primitives. And it's the implementation is verified, but there is no cryptographic security proofs. Because it's the job of cryptanalyst, I guess. There is also a paper whose informal name is Signal Star, which do a verified implementation of the Signal protocol in WebAssembly. So its specification closely resembles to a specification written in ProVerif, but there is no security proof done on the specification that is used to prove the implementation. Then there is some protocol security papers, such as the DY-star paper, that includes a proof of Signal. So this, I think the Signal specification in DY-star is not bit precise, which is something we improve. And then there is a paper about noise star, so a secure and verified implementation of the noise family protocols. So this one use two different specifications for implementation and security. So it's possible to eyeball them and see that it's doing the same thing, but it's not a single specification for both proofs and implementations. So we believe that we have improved the methodology to conduct security proofs on a cryptographic protocol. So now that it is set, I can do a brief tour of MLS. So MLS, we can divide it into three subprotocols. So there is TreeSync, which deals with authenticated group synchronization. So it means that group members agree on the internal cryptographic state. In particular, very important, they agree on who is in the group. Then there is TreeChem, which deals with efficient continuous group key establishment, meaning that this protocol will provide fresh group keys to the group member continuously during the lifetime of the group with forward secrecy and post-compromise security. And lastly, there is TreeDem, which deals with forward secure group messaging, meaning that given a key provided by TreeChem, it will allow group members to exchange messages securely with other group members with forward secrecy. So I will describe the three subprotocols in the reverse order. So first TreeDem, then TreeChem, then TreeSync. And I will make a few simplifications because the protocol is very complex and this would require a lot more time to properly explain everything. So I will assume that there are a power of 2 number of participants in the group. And in practice, all my drawings will be with n equal 2, so 4 participants. And so it means that we won't see what happens with dynamic groups when people join and when people leave. And so this is to ensure that I don't fry your brain with these explanations. And but I believe it still gives the core idea behind MLS. And so it's a necessary first step to understand the full MLS protocol. So now that this is said, let's talk about TreeDem. So TreeDem is a protocol that allows group members to exchange messages in a forward secure manner. And for that, it uses a group key provided by TreeChem. So here it's the R key at the top. And the idea is that we can do something similar to sender keys by deriving a sender key to each participant in the group. To do that, we can use a keyed hash function and use it on the group secret. R. And so you compute the hash function with the key Alice to obtain Alice's key. Same for Bob, Charlie, and Dave. And next, from these participant keys or sender keys, we can derive a full stream of keys by hashing these keys. So at the beginning, we store the keys A0, B0, C0, D0. And when Alice sends a message to the group, she will use the key A0 to send message to everyone. So all those keys are known by everyone in the group. So Alice can use it to encrypt, and other group members can use it to decrypt. And then she will use an operation which we call the forward rotating. And now everyone will store the key A1. So what happens here is that from A1 you can deduce A2, A3, and so on by applying hash functions. But because hash functions are not invertible, we can't deduce A0 from A1. So this helps for forward secrecy. Now, if this state is compromised, then we are not able to derive A0 from it. Hence, we are not able to decrypt the message sent by Alice. And so, same stuff happens when compromise. So we take the cryptographic state of some of the participants and leak it to the adversary. So here, by compromise, I say that the adversary will obtain the knowledge of the keys stored in the device. And so here it's what's in circles. So the attacker will obtain the knowledge of A1, B0, C0, D0.
You cannot recover A0.
Yeah,
Okay, that's fine.
And so this state of stream of keys will evolve. And so when Charlie sends a message and then another one, the state will evolve, and we will only store the latest key for everyone, ensuring that we can't recover keys that were sent before. Yeah.
So to get post-compromise security, don't you have to add in something else here?
Yeah. So Tridem doesn't do post-compromise security. It's just a job of Trichem.
I see. Okay.
So Trichem will provide post-compromise security. So it's the healing thing I talked about. I said that messages are secure after a period of healing. And so what will happen is that a group member will at some point say, okay, I want to hear about a compromise, do some operations in Trichem, and this will provide post-compromise security.
So that rotates this R value here, or does it rotate the IC? Okay, and then you just redo this within those.
Yeah.
Okay.
Trichem is coming right up, right?
Yeah, so Trichem is the next slide.
Got it.
A few next slides. Okay, so if you are following closely, this protocol is called Tridem, but there are no trees. So why did we call it like that? The answer is that it's a simplification, and in the protocol, there is such a tree. So this is an optimization because in the case where you have a very large group, but only a few people talk. So here, when you have the R value, to ensure forward secrecy, you must erase the R value. Otherwise, you can recompute all the stream of keys, which means that because you have to erase this R value, you have to compute the sender key of every participant in the group at the beginning. And if only a few people talk in the group and most of the group members don't say anything, then it's not necessary.
Sorry, I think I missed something, which is I never quite understood why you need different branches. So I understand within one branch what it's doing.
Yeah.
What are the different branches?
So it's for concurrency issue. So we want everyone to use different keys. we want to avoid a key to be reused. And so if Alice and Bob, if we only had one stream of keys, then Alice and Bob could want to send the message at the same time and use the same key. So,
So if I have, say, a group of 100 people, should I expect to have 100 branches?
Yes.
Okay.
So I guess I'll say it in the mic because if we have a group with 100 of people, then we have 100 branches and 100 stream of keys.
The important point here, if I may add, is that this is all lazy, right? If you look at the next slide of the tree, it's that you only compute it as a recipient when you need to decrypt the message from Alice, and the tree structure helps you make sure that you don't maintain n ratchets in parallel for everyone in the group.
And then as a sender, I always stick to one branch.
Not sure what you mean.
So if I am a sender, which branch do I pick when I'm
So you pick
data?
your branch. So
Okay,
if you are
I have
Bob,
one branch and I stick to that.
you are Bob and you use only your branch to send messages.
Everyone is always at a constant position in the tree, so if you're Alice, you live bottom left, you have your own series of hash derivations and ratchetings, and that's your own stuff. And conversely, there's enough information for other members of the group to reconstruct that information to decrypt the messages you sent.
So suppose that I want to ratchet, okay? So I'm Alice, I want to ratchet, I'm on the left branch.
Yeah.
So I send you a message with a new key in the left branch. Do I also send you an information saying, by the way, this is with a new ratchet or something like that? Or
So
is there a special command that I say, let's ratchet?
So Alice says, I'm using the key 0. And then people will know that they have to use this key. For example, to deal with bad message ordering, you want to know which key you are using. And then once people decrypt the message with this key, they will delete this key and use a ratchet forward and only store the keys that comes after.
Okay, so you mentioned something interesting, which is this idea of ordering constraints. So when do I know that it's safe to delete an old key? Because I might still receive a message that was encrypted with the old key.
Okay. So this is the drawing is a simplification here. We don't use A0 or A1 to encrypt. This is a keyed hash function again. And so we have this in Signal, I think they are called the chain keys because you chain them, and then so you derived both the next chain key, but also a message key that you will use to encrypt. And so if I receive a message saying, oh, I will use this message key way further in the future, then what you can do is to derive all message keys in between and store the next chain key so that you still have forward secrecy and you will only
To your question, I think it's an application-specific policy. It's the same thing as in Signal. You may want to have a more conservative policy to deal with out-of-band messages or messages that were delayed in transit, but that's called the delivery service in the MLS standard, and that's left outside of the scope.
And actually, if you look at the double ratchet specification in Signal, there is a special section about so what do we do about out-of-order messages? So it's as Jonathan said, more on the application side than on the cryptographic side. So what do we do about groups with only few people talking? So the idea is to use a tree. So first, nobody is talking, so we only store the root key. And so to obtain the sender key of a participant from the root key, we will do a series of ratchets following the tree structure. So here the hash function is keyed by either I compute the left hash or the right hash. And when Alice wants to talk, so we will compute x and y and erased r. And then to obtain A0, we will compute A0 and B0 and delete X. And like that, we obtain the key of Alice without computing the key for Charlie and Dave. So if we look closely at the complexity, like the computational complexity of this, to compute a root key, the participant key from the root key, in the worst case scenario, we need log n hashes, where n is the number of participants. And so we might think it's bad because before it was constant time and now it's logarithmic. But if we look more closely, if we ultimately derive the keys for all participants, then we do a total of so 2n hashes, because it's a complete binary tree, balanced. So if you have n leaves, you have n minus 1 internal nodes, and so you do a linear amount of hash computations, which means that on average we only did one hash, a constant amount of hash for each participant. So here, to gain an intuition of why it's not that slow, when computing the key for Alice, we did 2 hashes, but then we also got the key of Bob for free. Now obtaining the key of Bob requires 0 hash. So when you compute the key of someone, then you propagate some information down in the tree, and so in practice you have an amortization phenomenon, and it's not that slow. So that's it for TreeDem. Now we can move on to TreeChem. So TreeChem.
Previous one did not consider the idea of changing group sizes, right? Like a new user is added or a user is deleted, because that would change the size of the tree. Might not be complete.
So this is out of scope of the explanations that I want to do here. If you are interested in that, we can talk about it later. But for the purpose of this talk, it's too complex.
That sounds good.
Yeah. Okay. So now about TreeChem, so which gives forward secrecy and post-compromise security by providing the group fresh keys. The initial idea that was used in the first draft of MLS was to use a tree of Diffie-Hellman. So the idea is that with Diffie-Hellman, so for Alice, there is a private key A and the public key G to the power of A, and you do a tree of Diffie-Hellman keys. So to obtain so the invariant is that the private Diffie-Hellman key of a node is known only by the participant located at its leaves. So, for example, the X here, it's the shared secret between Alice and Bob. So if you know A or if you know B and the public information which is in the squares, then you can compute X, which is J to the power of AB. And all the way up to the top, you can obtain the root secret, which is Z. So here it's a simplified version because in practice you have a whole key schedule. So Z is the input of the key schedule, but for a simplification purpose, I didn't put it in the diagram. And that's it. So if Charlie want to heal from a compromise, then she will update its private key, and so it will be C prime. And then the shared secrets will change along the path from Charlie to the root. So above it, there will be a new private key, a Y prime, and the new group key will be Z prime. And so Charlie just need to publish all the public keys on the path, and every group member will be able to compute the new group secret. if you look at the complexity of this, to send, we need a logarithmic amount of operations, and same to receive. So the idea is that asymmetric operations like diffie-Hellman cost a lot of computational resources. And the design of the actual TRIChem exchange asymmetric operations with symmetric operations that are more fast to obtain a receive complexity of one asymmetric operation, which is nice because one person send, but all participants receive. So we want to have fast receive. So in the final design of TRIChem, we use, so not diffie-Hellman keys, but asymmetric encryption keys. For that, we use the HPKE standard, and we use hashes. So before, the invariant was that the diffie-Hellman private key of a node is known only by the leaves under it. And so here it's the same, but with private HPKE keys. So to update the keys, we do similar thing by updating keys along the path from a participant to the root. So if Charlie does an update, Charlie will do it in 3 steps. First, it will generate the new keys, encrypt the keys to the people that should know these keys, and then publish the public information. So in the generate step, Charlie will generate P0 and hash it to obtain P1 and hash it to obtain P2. The idea being that from P1 you can compute P2, but you cannot compute P0 by non-invertibility of hash functions. Then you can encrypt P1 to Dave and encrypt P2 to the public key of the node X. Like that, Alice and Bob will be able to know P2 because they know the private key of X, and Dave will be able to know both P1 and P2 by doing a hash on P1. And then once we have all the P0, P1, P2, we derive public and private keys from these values. So now to send, we need to do a logarithmic amount of encryption, but each person has to do only one decryption, which is a performance improvement. So that's it for the simplified version of TRIChem. The actual one is a tad more complex, but the idea is still roughly here. So now I can talk about TreeSync, which deals with ensuring that members of the group agree on the internal cryptographic state. So why is it important? This is when you join a group, you receive a tree with a bunch of public keys, and how do you make sure that those keys are not controlled by the attacker? And in fact, the problem is more fundamental. How do you make sure that who is in the group? Can the attacker be in the group without you knowing? Or do you know that Bob is really Bob, or is Bob the attacker? And so TreeSync solves all these problems. So TreeSync authenticates TRIChem state. In particular, it authenticates all public keys along with the recipient. So who is able to decrypt the message when you encrypt it to one of the public keys. And it also authenticates the group roster to ensure that we have group membership agreement, meaning that everyone agree on who is in the group, which is a highly important feature of group messaging, because if you don't know who you are talking to, then why bother doing encryption? It's the same ideas, for example, with TLS, so which secures connection with HTTPS. You have this certificate thing where the server certificate will authenticate the internal keys used in the protocol. And so before the existence of this tracing, there were many attacks discovered in MLS, which roughly looked like man-in-the-middle attacks. And now with the integration of tracing in MLS, this class of attacks don't exist anymore. So let's see a simplified version of tracing. And so the naive attempt would be to say, okay, suppose Alice is the last person to have done an update to the group. So Alice will include a signature of the whole tree. So it signs the public keys, but also all the group members, like the identity of all group members. Now, when Charlie modifies the group, it will also include the signature of the whole tree. But now you see that we went from TZ to TZ prime. And now in this state, group participants don't remember what is TZ. So it is not possible to check the signature of Alice because it covers TZ, which is not something we know anymore. And this is bad because now the tree, so the subtree rooted at the node X, which I called TX, is not authenticated by Alice anymore. And so we can imagine an attacker to tamper with such a tree. So the idea is to avoid this problem, to include one signature for every subtree above each leaves. So here, Alice will sign so TA, so her own leaf, TX and TZ. And when Charlie does this update, then so the signature of TZ in Alice will not be intelligible, but there will still be the signature on TX that people can check. So the invariant is that every subtree is signed by one of the leaves under it. So here it's true because X is signed by Alice, and Y prime and the Z prime are signed by Charlie. So it's a bit dual guarantee with TRICAM. So with TRICAM, it guaranteed that the private material in the node was known only by the leaves under it. Here it's an invariant saying the public key at this node was written by one of the leaves under it. So it's a read-write duality kind of things. And the complexity is a bit sad because you need a logarithmic amount of signatures in each leaf. And so I talked about the duality with TRICAM. So here we can do the same thing. We can trade asymmetric operations, such as signatures, with symmetric operations, such as hashes. So this slide, so I tried to do my best to make it understandable, but it's a very complex topic. So if you don't understand all the details, this is normal. So, okay. In each node, we will store a new value, which we called parent hash. And so Alice will only sign the content in her leaf and her parent hash. And so what does the parent hash value covers? So the parent hash in Alice covers the content of the node, her parent node. So its key, its public key and its parent hash, and will also cover its sibling subtree. So here the tree rooted at P. And the parent hash at X will cover so the content of its parent, and the subtree, which is its sibling. So here, the subtree ty. And when Charlie do an update, Charlie we do similar computations, and here we see that the parent hash of Alice still authenticate the tree rooted at X. So we have a new invariant, which is that every subtree is linked by parent hash to one of its leaves that ultimately signed this parent hash. So the result is that every subtree is authenticated by one of its leaves, which is the invariant we had before. And the complexity is very nice. We only have one signature in each leaves. So based on what you understood of these slides, so either you understood everything and that's great, I'm very happy. And if you didn't understand, I hope this is convincing to you that it needs formal verification. So that's it for my description of MLS. So what did we miss? So there is a concept called blank leaves. When you don't have a power of 2 number of participants, you just say that some leaves don't store any content. They are blank. Next, we have the concept of blank nodes, which is that when you remove someone, so you blank its leaves, and you also blank the content of all the nodes where it might know some of its secrets, to ensure that we have a tree with no secret known by the removed person. Then, when you add someone in the tree, so the invariant of tricking was that the private key was known by all of its leaves. But if we add someone, then we break the invariant. This person doesn't know the secret. So what should we do to restore this invariant? Should we blank all the nodes where the new participant doesn't know the secret? So we don't do that. There is a concept of unmerged leaves, which are the leaves that don't know the secret of a node yet. And next, there is a concept of filtered nodes, where 2 nodes cover the same set of participants, and so we can optimize away some of the nodes. So, yeah.
Just to clarify the unmerged leaves thing, you're saying that that's where, like, when you add people, you just like encrypt the secret to them directly, as opposed to including them in the tree, because including them in the tree would be inefficient, and you wouldn't want to do that immediately.
So the idea is that when you add someone, suppose you add someone in one of the leaves, then when you will encrypt some secret to a node, then the leaf doesn't know the secret of this node. So the idea is roughly to store in each node the set of leaves that don't know yet the secret and encrypt it separately.
Encrypt it separately to each node, so
Yeah.
it's like linear in the number of unmerged nodes.
Yeah.
The cost of updating the secret.
Yeah.
But eventually you'll want to merge them so that you can
Yes.
make use of like that logarithmic
Yeah.
advantage of MLS, right?
Yeah.
I'm just waiting for someone who's already in the group to be able to authenticate them, and eventually they will be assigned reviews.
I see, okay, thank you.
So now that you hopefully understood everything about MLS, I can talk to you about the contributions we did on TreeSync. So the first contribution was to modularize MLS into 3 subprotocols. And at the beginning, when we tried to modularize it, we found it was not possible because we couldn't have proper abstraction boundaries. So, for example, concepts like deep concepts of TreeChem were used inside TreeSync, which couldn't result in a very nice modularization. And so we proposed changes of MLS to the working group to be able to have a very nice modularization. And the working group accepted those changes, which now means that even if the RFC is still described in a monolithic way, it could be described in 3 nice subprotocols. which we do in our specification that can be seen as a reference implementation. Next, we fixed the invariance of tracing. So I talked about the parent hash invariant, that every node is linked by parent hash to one of its leaves, but also there is invariance that at all time, all the signatures of the leaves are valid, and other checks on unmerged leaves. And so when people join the group, they check that those invariants are true. And if those invariants are not true, then the group is malformed, maybe was created by an attacker, and so group members will refuse to join the group. And so, so something we want is that a well-formed group can become malformed after doing some modifications, such as adding or removing people. And so we want that the invariance checks are actually invariants under group modifications. And so it was not true. The invariants were not invariants, and you could take a well-formed group and transform it into a malformed group. So we proposed fixes to the working group by strengthening the invariants so that they pass the induction, and this was accepted by the working group. Then, yeah.
Just to make it clear, was it that the implementation or like that was proposed was somehow correct, but it just the well-formed check wasn't like strong enough inductively, or did you have to fix also the implementation, like the theoretical implementation?
So I'm not sure I understand.
They took fixes to the spec, right, to enforce the invariance.
Yeah. So the fix was on the spec,
Okay.
and it goes through the implementation then, because
So you had to strengthen the invariant and refine the code so that the code would respect the invariant.
But it's about like the last sentence. A well-formed group could be malformed.
Yeah.
Just based on the invariant, or actually in the implementation. That's just.
Previously, the spec was not enforcing the invariant, and because the implementations were correct with regards to the spec, it would create a malformed group.
So this was when we tried to do the functional correctness proofs. So when we did the security proofs, we found that the MLS specification tries to give intuition on the guarantees offered by parent hash. And so the problem is that those guarantees are described in an imprecise prose. And the second problem is that those guarantees were not true. Because so in the examples, so when I described tracing, it is true, but because of all the complexity with block nodes and filter nodes and things like this, it had actually weaker guarantees. And so we fixed the parent hash construction. We submitted the change to the working group that accepted it. And lastly, we found a signature ambiguity attack between tracing and 3DEM. So I didn't talk about it, but 3DEM also do signature to authenticate messages. So both protocols internally rely on signatures. And because you don't sign high-level data, you sign bytes, sequence of bytes. So you need the serialization function to convert high-level data into sequence of bytes. And the problem here is that both sub-protocols use the same signature key, but they use different message format types, meaning that even though they sign different type of high-level data, their byte representation could be the same. So what happens if we have a collision on the serialization function? Then it results in a bad interaction between tracing and 3DEM, because an attacker could take a signature computed in 3DEM, so on message 2, and inject it inside tracing as message 1, merely resulting in a signature forgery for message 1 in tracing. Yeah.
Someone who is not an expert in formal methods or programming languages, how does one identify these kinds of issues? For example, this one, is this something that just shows up like when you write the spec, you realize you cannot prove it?
Yeah.
Or like, do you guys have a different approach to identifying these issues?
Yeah, so this we found it while doing the proofs. So when doing the proof, so we didn't prove tree them yet. So, but when doing the proof of tracing, we thought, okay, what are the minimal assumptions we make about other protocols? And we make the assumptions that they don't sign data that can collide with tracing. And so we found that by doing the proofs and thinking, this looks shady. And then we thought a bit about it, and so we saw this attack, and we showed it to the working group that immediately reacted to fix this attack.
Can I ask if were you able to implement this attack, or is there, I guess, an example of you have these two messages that collide in their encoding, and what are the implications of that?
Okay.
Signature forgery.
So we found that. So we first found that nothing was done to make sure that there was no collision. Then we were thinking, okay, so does by chance we avoid collisions, or is there collisions? So we wrote a program to find such a collision. And so then it will require more work to transform it into a practical attack. So this would have been very interesting, for example, if the protocol was standardized and deployed. But here, because we were still in the standardization process, this is enough. We just showed that to the working group and it accepted. We didn't because in this kind of attacks, you often need to still do many computations to transform it into a practical attack, and here it would have been a loss of time, so we didn't do it.
Yeah, that's funny because a lot of the other, like you mentioned, the matrix attacks, and there's also the Threema paper. A lot of those attacks have to do with this domain separation issue and like using the same key everywhere. So it's
and so in the Threema papers, they have to do many
expensive computation to find something that's like the
many
right
computation
fault.
to find a public key that has these properties and to create actually useful collision. But here we didn't bother to do it because it wasn't
Just
useful.
fix the spec, right?
Yeah. So this is and so so we fixed it. And so this attack. I might note that we found it because we did proofs on a bit precise specification. Because if we were to work on a slightly simpler model, it would have been very easy to have a specification without this attack. And we ensure that we have bit precise specification because we can execute it and do interoperability tests. And now, if you still have some brain power left, I can do a quick sketch of tracing proofs.
So you just hit the hour mark.
Ah.
So maybe that would be something that you can go over offline.
Okay, so you can see the beautiful slides. Voilà. And so just as a final note, so this is the proof effort. So I spent roughly 2 years working on this. Which took time because first this is a bit protocol, so it takes a bit of time, but also we had to develop the methodology to treat large protocols like this. We have to work on seeing how to do proofs on a bit precise specification, which is novel work. Then we have to do a lot of code on the side to make sure it was doable nicely. So, for example, we had to develop a message formatting framework that work on both concrete and symbolic word, and also the specification is a moving target because it evolves during its standardization, and so some time was spent just implementing the changes that other people did to the protocol. And that's all for me.
Do we have time for questions?
So we still have time for questions in the room, and I'm also keeping an eye on the chat online if anyone wants to ask an online question.
Okay, so one thing is the MLS RFC still considered sort of in progress, or is it considered finalized?
No, it's published.
Okay, so and following up on that, I mean, because when you were proving correctness of tracing, you found some issues in it, right?
Yeah.
Those were backported to MLS. I mean, do you expect to have the same situation with proving tree chem and tree dem?
Okay, so as a special thing with tracing is that it was a bit a dark corner of the protocol. It was not studied by the cryptographic community too much. All the focus was on tree chem because it's like the fancy part of the protocol. There was some focus on tree dem, and tracing was a bit understudied. So which is why we tackled it first. On tree chem and tree dem, there are a lot of pen and paper proofs. So everything is not on my shoulders. It's a community effort, and so I expect to find, and I hope to find no problem in tree chem and tree dem. Yeah.
So I guess you built your security proof on top of DY-star. Did you have to extend it, or did you use basically the framework as it is? And
So we had to slightly modify it. So yeah, we had to do slight modification to integrate our message formatting framework. But it's we almost use DY-star as is.
a bit of a follow-up on that. Do you see potential issues in doing the reasoning like symbolically, like attacks that maybe could exist if you think about the computational model that are ignored here? Or do you think, like, do you have an intuition of how sufficient it is?
So on tracing, the nice part is that most of our proofs are actually computational. So we were able to because to do security proofs, you have to decide on an attacker model. I mean, a security model, and we were able to push the decision very far in the proof. So the difficult part of our proofs are true in the computational model. So it's showing that if you are able to construct this thing, then you are able to construct a hash collision. So this is true in the computational model, and we use it easily in the symbolic model, because in the symbolic model, hash functions are injective, so you don't have any collisions. So tracing, I expect that there are no issues in the computational model.
Do you also use, for example, the fact that, I guess, hash functions are one-way functions?
So this is not needed in tracing. So tracing is only authentication. So
Oh yeah, I guess that was the which one?
for TreeChem and TreeDem, we export this. Yeah.
So we have an online question actually. Marcus asks, does the MLS standard committee use any formal technique to verify its standard, or just pen and paper? And you could have answered that, right, when you said that we're doing formal for TreeSync and the others are doing more pen and paper stuff for the rest.
Yeah, so I would say that the MLS committee isn't doing any things on its own. It's like researchers independently that so do such proofs, so such as me, but such as other cryptographers. And eventually, those people can get involved in the working group, but it's not the working group itself that is doing proofs.
So one question I have is, here you prove that bad things cannot happen. Could you also prove that good things do happen if everybody does the right thing? So that probably requires some temporal logic, reasoning, and stuff like that. So for example, it would be something along the lines of, if Alice sends me a message under some ratcheted key, if I follow the protocol, I will be able to decrypt that message.
So it would be possible to do it, but so it would be on the 3chem and 3dem side, which we didn't do any proofs for yet. So neither security, but so this would look a bit like functional correctness. I mean, this is how we would call it.
Well, but this is a temporal aspect, right? You would say eventually this will happen. You know? So you have to.
You could do it in a deterministic way if you said, you know, I'm going to revisit all of the ratchets, I will find one. You would just hit the function terminates and
So
finds the right result.
I would say if Bob encrypts a message, then all the people will be able to decrypt it.
And the will be able involves like another recursive traversal of the ratchets, and we show that the function eventually returns a success, which means that so you don't necessarily need to introduce the temporal logic at this point.
And I know nothing about temporal logic, so.
Just computers like eventually.
Yeah. Okay. Yeah.
Do you think these verification tools could also be used by cryptographers in the process of designing protocols, like as opposed to like they come up with something and then later on they worry about if they can prove that it's secure? Can you incrementally build up a protocol and verify things along the way? Or is that something that people have explored or that exists?
So this is roughly what we did here. So we arrived early in the standardization process, and so we were able to propose changes to the protocol guided by our formal proofs. So we had to develop the methodology to be able to do it for such a large protocol. So now I think it requires a lot of expertise. So at this day, I don't think we can say that anybody doing a protocol could verify it in this way. There are other tools which are more automatic, like Provery for Tamarin, which I think you can use with less expertise. And so it will be a future work to see how to make this methodology easy enough so that many people can do it.
It's an open research question, right? Like you have a DSL that would allow you to do secure by construction protocols, and that's kind of what you had in mind for your eventual post-PhD work that you're telling me about, right? Like that, making this a lot easier and a lot more automated.
Usable by other people.
Yeah. Some people are able to use some of the more like automated tools, like you said, Tamarin. Like if you do a little bit of training and learning the tutorial, some people are able to do a little bit of it. But this requires some deep expertise.
And I've heard there are people they build compilers from like protocol specifications to like cryptographic protocols that also give you a proof or something like that. That's kind of like another far end. But
That I don't know about, but I'm curious too.
sure, yeah.
So you mentioned that Signal, because Signal does have group chats, that they do pairwise exchanges, and Matrix also has some kind of E2E thing that they came up with. Do you know if either of those are interested in incorporating MLS?
So Signal, I don't know about it. Matrix are interested in MLS. And so actually there is a whole working group which is called MIMI for more interoperable messaging interoperability. Because there is these laws in the EU saying that big messaging applications should interoperate. So this is an approximation because I'm not super familiar with it, but so there is a working group which wants to create interoperable end-to-end encrypted messaging applications, and which would use MLS as which are considering to use MLS as a backend.
So one thing to add is that MLS does not have any notion of federation, or like it's not like there are interop like parties just to make sure you got the implementation right, but it's not intended yet to to be like across multiple instances.
Yeah.
That's what Mimi is about.
So yeah, so MLS is about sending messages to say sending byte sequence in the group, but it doesn't say how to deal with groups with like administrators, how to deal with you send a message, but you can also send an image, you can send a file. It doesn't say anything about this concrete real-world considerations. It mostly considers how to exchange a sequence of bytes in a secure manner. And the Mimi working group is working on all the features people will want to use in actual messaging applications.
MLS doesn't even say, once you've crafted your MLS message, how to deliver it with a header that says, you know, like who the recipient is or anything. That's entirely like application specific. Yeah. Any other questions? All right, that was great. Thanks, Théophile.
Thank you.